Hi, I'm Guang, 15 years old. In this lesson, we'll be taking a look at physical chemistry. We're still on the part with the Maxwell-Boltzmann distributions, alright? So, in previous lessons, we did have some different types of formulas and prove them, alright? But now, we will be taking a look at something a bit different. And in this case, it will be something that you might know very well, which is the Graham's law. So this is what it looks like when you write it out. Of course, there could be many different forms, and this is just one of them, which is also one of those that are simpler to understand, alright? So, what is so special about the Graham's law? Now, Graham's law, let's say you have two different types of particles. Well, mainly you'll use them for gas, alright? So, a gas, you leave a gas in a space. Let's say you limit it to a corner of, let's say, a cube. Well, after some time, when you check back on it, of course, it would kind of spread throughout the entire cube that you have, right? So that will be what we call diffusion. Well, there is another term, if you can recall from previous lessons, which is similar to diffusion, but there is a difference between it and diffusion, which is effusion. So what's so special about these two? Now, diffusion is more generic. You just place a gas in anywhere, you release a gas from anywhere, and it just spreads throughout the place. But for effusion, you have a specific container that has small holes, or small pores, or a porous container, whatever you like to call it. And these gas inside will have to escape through these tiny holes. So that is pretty much the main difference between diffusion and effusion. Of course, for diffusion, you can also have holes, but these holes are generally bigger ones, or even just the entire thing, the entire wall is a hole, which means there's no walls, alright? So, easy examples of diffusion, let's say you're cooking, and you can smell whatever food you're cooking, so that is diffusion. Well, and then suddenly while you're cooking, you smell something a bit suffocating, and you hear a hissing sound, and you realize there's gas leaking from the can below. Well, that would be your effusion, alright? So that is a simple application of how diffusion and effusion can be used in real life, or happen in real life, alright? So, for Graham's law, you can use it for both diffusion and effusion. Yes, you can use it for both, but let's say you're doing a normal paper, or just those kinds of papers you have in school. You might start from diffusion, since it seems easier to understand, right? Since normally what you see is, let's say you have a tube, on one end you have a certain type of gas, on another end you have a certain type of gas, and they ask you, after some time, well, would they have a chemical reaction that creates a new substance, alright? And that substance would usually show like very different marks to be more obvious, alright? So those are some simple uses of how you can use the Graham's law. So, of course, if you want to exactly measure this Graham's law or do experiments to show that it is experimentally right and viable, normally you would choose to use effusion, since in effusion they go through small holes, which means that they're generally more spread out, so the gas particles within can't really affect one another anymore, alright? Since in diffusion, it is more likely for particles to collide into each other, and well, if you want to know how they go, it's either you want to study their free path, or even more complicated will be something like chaos theory and all, okay? But those will be something very different, alright? So, now, Graham's law, we will be mainly thinking about it for effusion. So, how exactly do we derive the Graham's law? Now, you have two different types of gas. Let's think about one type of gas first. Now, this type of gas, it spreads. So, how do you calculate exactly how fast does it spread? Now, in previous lessons, we have repeatedly used one thing for gases, which is the kinetic energy for gas, for one particle, or for many particles, alright? So, we can use that here. Now, what exactly are we going to see? Let's say we call these two types of gases gas A and gas B. If we take a look at gas A, then what you're going to see is half, let's say, Ma. So this M is the mass for one particle, alright? So this M is the mass for one particle. So Ma. So what do you have? Half mv squared, right? So you will be seeing v. Normally we would be using your root mean square speed. Alright? So your root mean square speed for particle A, alright? And then squared for your kinetic energy. Right, so this is what we have for your gas of type A. Now, you would have something similar, but for gas of type B, which you also have half B this time. So V root mean square for B and then squared. So what would be so special between them? Now these two, they would actually be equal, alright? So why exactly would they be equal? Well, they're under the same types of conditions, and under the same types of conditions and whatever kinetic energy conservation you have for everything, the kinetic energies would be equal, alright? What's different would be their masses and their velocities. So when you try to make an equation between these, of course you could leave it at m, or you could try to change the m a little bit. So m, although here you can use your mass for one particle, how about let's use the molar mass? So what's so special about the molar mass? Now you would have your molar mass for particle A, and this has to be divided by your Avogadro's number. Since these two halves, they will pretty much, well, since you're solving an equation, you can just simplify them out, alright? So molar mass for A divided by the Avogadro's number would actually be your mass for one particle of A. While the V's, you could let them be, you could still keep them. Alright, so this is not MB, I'm sorry about that, it's just Avogadro's number. Whoops. Okay, so here is what you're going to see. Now of course Avogadro's number, you can pretty much simplify them out again since it's just a constant. So what else can you find over here? Now let's say we put the molar mass of A divided by the molar mass of B. So you divide this. That means you can divide this to the other side, which you'll be seeing V square and V square. So this is what you are going to have, alright? Now, the root mean square speed for B and the root mean square speed for A, you realize they're pretty much, for A, it'll be inversely proportional to it, alright? Okay, so you can square root both of these sides, and what happens when you square root both of these sides? You get V root mean square speed for B divided by your root mean square speed for A, and this is equal to the square roots of your molar mass of B to your molar mass of A. Alright, so now what else can you see for this part? So with this, since it's a B, it will be on the other side, sorry about that. So molar mass of A over the molar mass of B. So this is what you will see. But you might be wondering, well, how can it relate to this formula that you actually have up here? If you think about that question, it's pretty simple, isn't it? Since if you have two gas and you release them at the same time, and they travel to a certain distance, wouldn't the time be the same? It would be, since you release them at the same time. So that means whatever time passes, it will be the same. And since this would be your speed will just be your distance divided by time. And since time taken is the same, you can just change this into the distance traveled. Alright. Okay, so yes, you can change them into your distance traveled. Now that's one way to change that. Now what are some other ways that you can change it? Now, molar mass. What if, let's say, you don't want to use your molar mass? You could, of course, use, let's say, if you're just given a density, okay, using rho for your density, or even you're just only given your mass for one particle of each type. So yes, you have all these things that you can use, and it's pretty much proven. Right, now how about let's put this into use. Now let's say you have a little container that you have chlorine gas, and another little container with argon gas. Alright? So when you release your argon, you release the argon from this little container, and by release it is more of an effusion. Alright? So effusion, that means it has to travel through this little wall with little holes inside. Okay, so let's say you're given this argon gas. It goes through at, let's say, 4 millimoles per second. Alright, so if you're given the argon gas can go through at 4 millimoles per second, what will be the speed of your chlorine gas? Alright, so the main thing here would be using your Graham's law. Now Graham's law, it is not necessarily a distance, as it could also be using your speed. Okay, so you're trying to find the speed of chlorine gas. So when this is divided by your speed of argon, and beware, argon is a noble gas, so it's only AR, there's no AR2. And this will be square root of molar mass of AR divided by molar mass of Cl2. So for their molar masses, you could check the periodic table for each of them, and after you know what the values exactly are, so AR would be pretty much 39.95, while CL is 35.45. Alright, so one is 39.95 and one is 35.45. But you have to be aware, this is Cl2, so you have to multiply that by 2. So what you will get is, alright, so it will be around 3. Alright, so your speed for Cl2, since if you know how to solve simple equations, this should be obvious, which is going to give you around 3. Alright, or you could write 3.00, whatever you're given. Alright, so 3 would be just fine. 3 millimoles per second. Alright, so this is pretty much what we're going to see for this example. So you can use things as easily as this. Alright, now this will be the speed for your Cl2 if your speed for AR is this. And you also have to be aware that these two happen in the same conditions, because if you have different conditions, you might have to use some other different types of calculations. Alright, But that is pretty much all we're going to see for your Graham's law, right? Now what do we start with? Just a quick recap. We started with the kinetic energies of both types of particles. And using your kinetic energies, you equate them. You pretty much solve an equation, not exactly solve, but you try to change the equation into a form which you can more easily understand. You can understand it as pretty much like a ratio, or the square root of a ratio in this case, alright? And at last, you get whatever you want. Well, using this, you pretty much just apply a formula to whatever you need. Just be aware of whatever types of molar masses that you get, or whatever conditions that you have, alright? So I hope for this lesson, you're clear of pretty much everything so far, alright? I'll be ending this lesson here, and thank you for your watching.